Okay, good morning, everybody. I hope everyone's having a wonderful day. So, last day, we had started talking about this course, CS340. In addition, I started talking about a couple of concepts. So, the first thing I did was I talked about what a problem was, at least our working definition of what a problem was. So, in a problem, we have a set of problem instances, and each one has kind of two things that are interesting to us. But each one of these instances consists of inputs for that problem that they'll be encoded in some reasonable encoding scheme like binary, and hence they have a length we call the input size. And normally when we want to study a problem, we want to study the whole problem, which means we need to consider all the problem instances. So I thought I would give a couple of examples just to make sure that we have an idea of what I mean by a problem again. So the big thing I want you to notice is the idea of input and output, at least in this definition. So I thought I would draw on a couple of examples you've probably seen before. If you've never seen these before, either way, you'll see it right now. So the first one you naturally think of is sorting. So imagine I give you an array A and it has n elements in it. So you can think of the elements as integers if you'd like. And I would like you to return a sorted in non-decreasing order, where I assume that these elements are so-called comparable. So that means I could tell you which one comes before another element, or if they're equal so-called precedents. So in this problem, what would be, say if I give you an instance, what would it look like? It would look like an array, right? You may even give n along with it. But what would be basically the input size of such an instance? What would be the input size here? So I'll give you a hint. It's very similar to the first example I gave you last day. Yeah, n. Yeah, n. N is a reasonable consideration of the input size. Now, if you want to go real crazy and be like, okay, I'm going to literally say, okay, this is going to be the number of bits with respect to n, you can literally go through each one of the parameters, measure those things out, and you could do that. But you'll find that very often what we're really interested in are these core components. So for example, when we have an array A, that array A consists of elements, each one of some fixed number of bits. So if you think about it, you can think of like integers that are encoded with some number of bits, or like say they're like 32 bits long each. So if you think about that, okay, well, it's some constant times, well, each one's a constant size, and if there's n of them, then that means it's going to be n times some constant, if you think about the array itself. So just keep that in mind. That's a nice intuitive way you can think about this. I like to think about it like that, but one little kind of hidden assumption in doing this is I'm assuming that the machine is capable of reading words of any sufficient length as long as they're just some large size. So I can make it as big of a word as I want for my machine to read them. That's one implicit assumption I'm making with what we're going to be doing here. I'll talk more about that later. Another one here. Actually, can somebody tell me an algorithm that actually solves the sorting problem? Can somebody tell me in the chat one that you can think of? Merge sort. Merge sort's a good one. Bubble sort. Yeah, bubble sort would solve this problem. Yeah, those are good answers. Definitely. Selection sort. Yes, that's a very nice one. Insertion sort. Like, you got quick sort. That's another one. Excellent. I'm seeing a lot of great answers in the chat. Wonderful, wonderful. Yes, these are all ways you can solve this problem. Wonderful. Everybody's on the ball. See, like I said, you guys are all pros with this. Awesome. So another problem is the so-called search problem. I'm going to define it this way, but you'll find very often when we actually look at it, this S right here is actually going to be things like an array. It's just going to be represented as an array. If first this set idea here seems a little bit abstract, you can just think of it as an array if you really like to. So for a search problem, imagine I give you a set S of n elements and some element X. You can think of this as a key. I want to know whether X is in S or not. So you may know algorithms that can solve this problem. We'll talk about one depending on where we get to today, we'll hopefully talk about one. But can somebody think of one that I can use to solve this problem? So think of set S as an array. It's maybe one of the first algorithms you learnt in your studies of, yeah. So you could definitely, so I definitely see linear search in the chat. That is basically the one that I'm going to probably look at a little bit later on. Just to really get us all up to speed. At the same time, you may know other ones for more specialized kinds of inputs. For example, binary search is one of these. So you'll notice that I don't really give you any assumptions about the elements. I just say, okay, there's these elements. I want to know whether it's there or not. Now, in a problem like that, so if I want to consider, say, binary search, I have to do something actually to the input. So there's actually an intermediary step that I would need to do with something like that so it actually solves this problem. So, for example, you might actually think about this in actually two phases. You might have it where, okay, I sort it, and then I could use binary search, assuming all the elements are comparable, for example. That's how you can use binary search to solve this problem. But you might find linear search is just good enough. And in fact, it is quite good already. I'll give you some justification later on that linear search is probably the best you're going to do with unassumed data. So is everybody clear? Just the general gist of this framework. So I give you a problem. Problems have instances, and each one I can think about as a thing that I can feed my algorithm, and it has to produce so-called correct output. And if I can do it for all of them, then I could say I've solved the problem. So I'm going to kind of talk a little bit about that right now. So generally, when it comes to this class, and when you try to solve problems, because remember, this is a lot of this class, even though it doesn't state in the title, this course is very much about problem solving. To obtain solutions to problems, often there are two parts. So first one is naturally how you organize. So how to organize data. So you could think of these as, of course, data structures. So you would think about how you organize, you can access and modify said data. So a data structure, of course, consists of all sorts of interesting facets to it. In, say, CS210, you will have seen the concept of probably an abstract data type. So in that, you could think about it, I give you some specification of a set of operations, and your job is to implement each one of the operations. So with a data structure, you can think of it like a collection of problems, where each one, so my goal is to solve all of them, but they all intertwine with one another, each with their own trade-offs, typically. So you may be familiar with some data structures. For example, you might know of binary search trees. You might know about stacks. And you might know what a queue is, right? So these are examples of data structures. You can use different data structures for implementing given abstract data types. So for example, I can implement a so-called map or dictionary using a binary search tree. So that's one aspect to this. The other one, and this one you'll find that I'll kind of ease you more towards in this class, but we'll be seeing both of these, is how to solve a problem. So this is, of course, the other part, the algorithms part. So we'll be concerned with algorithms and the relationships they have with problems. So just to give you an idea, I'm just going to give us a working definition of what an algorithm is for this course. So this is the one you want to keep in your mind for this class. Like I said, you could go really deep with a lot of the material in this course. In fact, you might find if, say, you're really, really fascinated about algorithms, you may know of more exact meanings for some of the things I'm using and describing to you. But you'll find that this definition is pretty much a working definition that will apply quite nicely for every circumstance we're going to talk about in this course. So to give you a kind of a working definition, this is one that, say, algorithm researchers like myself would be happy to accept and use all the time. So it's an unambiguous, I'll spell out what that means, unambiguous, step-by-step procedure that takes an input or inputs from an instance and produces output for the problem instance. Just as a remark, output of an algorithm is called correct. It's called correct if it is the solution to the problem instance. So you'll notice that my kind of working definition that we're using here, it's very closely entwined with problems, right? Notice that, like, I talk about problems a lot in this definition that I'm going to be using here. Now, if you're not satisfied by this definition, there is a more exact definition, but you have to take a course like 411 to see that one. So that being said, are there any questions about my definition here, or are we crystal clear? So I'm going to elaborate what I mean by unambiguous in one moment. So if it's about that, I will explain that in one moment. Are we all good to go? Give me a thumbs up. It's very quiet today. Oh, okay, we're all good? We're all good? Remember, if, say, there's really something that isn't clear, that's okay. That's okay. Just put in the chat if you're not sure. Okay, so I want to talk about this unambiguous aspect of this, because for some people, like, you'd be like, okay, well, what the heck does that mean? Well, what we want to do is we want to describe algorithms in a way such that for whomever we're trying to describe the algorithm to, this step-by-step procedure, it is clear as day. There is no matter of way you can misinterpret what the algorithm is. So I want to make sure it's, I want to make sure that if you describe to me an algorithm, that it is crystal clear. There's no way you can interpret it in two possible ways or more. So for example, for a course like this one, we'll be, for example, I'll talk about it in a moment, we'll be using pseudocode quite often to describe algorithms. But at the same time, you also have to keep in mind that unambiguous just means without ambiguity. Ambiguity, of course, means that there's more than one way you can interpret the same thing, and we don't want that when we talk about an algorithm. Hopefully that's clear. So the reason why I say unambiguous is because depending on who you're talking to, you may have to get more and more exact with the way you define the algorithm. So for example, if I was talking to, say this class, I may talk about an algorithm a little differently than I would talk to, say, a bunch of algorithm experts, because they'll be familiar with a lot of the things that I'm describing in this course. So they may know what a linear search is, just like probably most people in this room would probably know what linear search is. So same idea applies. It's just that you don't want to have it where you have two people in a room and I describe an algorithm to you and it's unclear what it is. And it has to be that it's like there's only one way you can interpret it. Is that clear to everybody? Is that unambiguous? Perfect, perfect. So I'm just going to draw a very helpful picture to talk about everything we've talked up to this point. So remember I showed you this one before. So I have problem pi. I have a bunch of problem instances. And each one of these will be interested in two things. Now, I must stress that the problem instance itself is its inputs. But we're usually interested in two aspects of a problem instance in a class like this. So this is an instance X in problem pi. So, of course, it has inputs, or just a single input. That's what X is. And, of course, it has a solution. Now, as we progress in this course, we're going to see a lot of different kinds of problems. For example, we're later going to talk about optimization problems, where this framework is going to get a little bit more general, where instead of it just being that there is only one solution, there's actually a whole set of feasible solutions that follow rules or constraints of a given problem. And there's only special kinds of feasible solutions that have the best possible value called the optimal solutions. So you'll see how this idea sort of generalizes. So naturally, this is what you want to keep in your head. Then, of course, I have an algorithm. So here's my algorithm. I'm just going to draw it as a box. And it takes in inputs. So you can think of this just like in a computer program, or you may have a function, it has parameters. You can think of this as you're going to feed the input or inputs to the algorithm, like so. So I could just go I'm going to give, that's supposed to say give, it's sort of melted. I give it X, it does stuff. That's what the algorithm does, and it produces output. You might notice that I'm making one implicit assumption with my definition of an algorithm. Does anybody see anything I'm making that's very implicit about this process? It's something I just want you to think about it. It's not critical for a course like this, but it's something worth acknowledging, is that with this, what I've described here, it takes input and produces output. So you'll notice that the algorithms I'm going to describe here all have to terminate. Can they go on forever, or they have to terminate in some finite amount of time? There's no infinite loops, right? So it's going to be that they have to terminate in finite time. That's going to be an important facet of the algorithms we're going to talk about in this class. So it has to terminate at some point. And generally the questions we're interested in asking is the output going to match the solution? So hopefully this picture really helps put everything together for you. Is this clear for everybody? For some of you, this is going to be like, oh, Dan's just saying some basic stuff for me. For others, this might really help put together a lot of the things that you've seen in previous courses so that we can kind of build on top of everything. Are we all good with this? I just want to make sure that we're speaking kind of the similar language so that we can really start having fun with this stuff. Sure, I could explain it one more time. So I have a problem pi. So this is the problem I'm interested in solving. It has problem instances. Remember, this is a collection of problem instances. That's what pi is. And it could be a finite number, but typically for interesting problems, it is going to be infinite. So there's going to be many, many, many in here. So many that you can never test all of them. And what happens is each one of them has inputs, and that's how it's encoded. And the idea is that our algorithm is going to be fed this input. It does some processing, and it produces output. And what we're interested in is that output correct? Meaning it is, in fact, the solution to that problem instance. So this just hopefully gives you a big idea of what's going on here. So just to kind of summarize everything. So an algorithm solves pi if it correctly produces output for every x in pi. But yeah, no, so this should hopefully help put everything together so that we can now talk a little bit about something else. So I'm going to be shifting gears. Let me just make sure I got what I need in front of me. What we're going to do is we're going to talk a little bit about analysis. So let me just migrate over this way. So what we're going to do is we're going to be starting to talk a little bit more about algorithms in the context of this framework. So I'm going to start talking about so-called analysis of algorithms. So you can think of this kind of like as the next major chunk of this course. So some of this you're going to have seen before. Other parts I'm just going to make more formal. Like I said, I'm going to be building this layer on top of what you've seen in something like 210. So I'm going to start off with just revisiting one of the problems that we talked about earlier. So recall the search problem. So I'm going to assume that that set S I've talked about previously is just an array, because I can encode all the elements as an array, and that's perfectly fine for our purposes here. So assuming the elements are given as an array L of n elements, we know a classic algorithm that solves this problem. So in the chat, please flood me in the chat with this supposedly classic algorithm. So remember, I'm not making any assumptions about anything but it's an array of n elements. So I'm going to just assume that I have some way of knowing whether the element I'm interested in, the x one I talked about at the beginning of the lecture, is equal or not equal to the element in question. I see in the chat, it's linear search. Just a reminder, just to make it a little easier to recall what it is. So remember in linear search, because I feel like it's important that you see me describe linear search in English, and also I'm going to describe it in pseudocode, just so that you could see how I do that. And you'll notice that there's sort of an art to how you describe these kind of things. So hopefully you'll gain some appreciation from that. In linear search, I'll abbreviate this with LS just because I don't want to have you writing too much. In linear search, the algorithm scans positions I is equal to 0, 1, 2, all the way up to n minus 1. I'm just going to assume the array is indexed from position 0 up to n minus 1. Hence why I'm indexing it in this fashion. You can think of this as left to right. I'll put that in quotation marks. Remember, left to right can be perceived as something else. So I don't want to say like that is exactly what it is. When I say left to right, I mean left to right. left to right. And if A sub I is equal to X, then X is encountered. And position I is returned. That's all say returned. It's sort of going up the side here, okay? However, that's supposed to be a semicolon over there. However, and that melted in the microwave. However, if every position I equals 0, 1, 2, all the way up to n minus 1 is checked, then every A sub I does not equal X, and the algorithm returns -1. So if I described it to you like this, it should hopefully be something that if you read this, you'd have a general idea of what linear search is in English. So this is one way I could describe an algorithm to you. Now, when you write it in English, however, English is naturally for anybody that knows several different languages or comes from somebody with a different background, with a different language. Usually when you learn English, it's one of those supposed to things. It's one of these fun, oh, thank you. Yeah, it's supposed to be L. Perfect. Let's fix that. See, this is why you got to keep me humble. It's very important. L, I think I got them all. Yes, it is. Yes, it is. Somebody pointed out that I wrote A when it's actually L. Thank you. Like I said, it's very important. So for somebody that maybe isn't as familiar with like knowing how it goes from going from one language to English, English is a very ambiguous language where you have to really spend a lot of time pinning down context for things. So when I describe a word to you, I have to premise it with definitions that are clearly defined, which is true in a lot of languages, but people that maybe learn English as a second language, they may have some appreciation for the way I have to write things very carefully in English. So just to make sure it's clear, so let me just draw out an example. So imagine I give you L. So this is one example of a problem instance. So I have 2, 9, 12, 19, 20, 22, 29, 43, 48, and 60. So it's just a coincidence that it is sorted. So don't worry. It's just supposed to be just a problem instance. So here's an array here. So for example, if I said that X, if I gave as input L, maybe I might provide N, because it's one of those things that comes up every once in a while where sometimes you want to say what the length of the array is without having to define it prior. You may include that as part of the input. Some people will, some people won't. That's not a big issue. So X, I'm going to say for example, I have X is 12. So if I pick X is 12 as part of the input for this problem instance, so it's L and X like this, what should linear search return to me? So if this is position 0, that's position 1, this is position 2, 3, 4, 5, 6, 7, 8, and 9. Yeah, it should return 2. So this should return 2. How about if I gave you, say if X instead was 60. Nah, let's not make it 60. Make it more fun. Let's go 63. Say if it's 63. Yeah, this time it should return -1 because 63 does not appear in the array. Perfect, perfect. So let's now move over to, so this is one way I could describe linear search to you. Is linear search clear to everybody? Because that's one of the big parts of this lecture I really want to hit across, is that when you communicate an algorithm, it has to be clear to your audience. There's no wiggle room around how I can interpret the thing. So for those that are very anal about language, this should be like right up your alley. Okay. So oftentimes when we describe algorithms, we use pseudocode. Whoops, let me write that a little lower. It's supposed to say pseudocode. It's sort of, the P was a little higher up than I wanted it to be. So we often describe algorithms in English or in pseudocode. And the big idea here I really want to hammer in is that you can, of course, implement an algorithm and describe it in a programming language. But ultimately, in a course like this, I really want you to hammer in that we want to talk about the algorithms themselves. So not tethered to some machine-dependent implementation of them or some specific programming language. I want to be able to describe to you the procedure, but I don't want to tether it to a given implementation. Is that clear to everybody? So I'm going to be I'm trying to distance the algorithm so I could study the algorithm itself. So that being said, I'm going to say instead of writing, we'll say writing here, instead of writing computer programs in a specific programming language, we use pseudocode. Now, you might ask, Dan, is there some convention to pseudocode? So you got to think about pseudocode as something that's meant for humans to read, as opposed to something that's specifically for a computer to read. So it should be unambiguous, but it's meant for a reader, not necessarily a computer. So I'm going to say there is no standard way to write pseudocode but, so I'm going to give you a big but here, big buts. Big but, you will find the conventions many use easy to adapt or follow. So why? Because very often pseudocode just picks up paradigms and control structures and everything that you are common and familiar with from programming languages. Has anybody here in the chat or in the class here, has anybody seen pseudocode before? So this isn't like specifically, so it isn't just like source code. It's something a bit more abstract. Okay, good. Yeah, so I've seen one or two no's. That's okay. That's perfectly fine. I see a lot of yeses though, so which is great. So if you've seen one way, you might see it a little differently here. If not, it may look very similar, and that's okay. That's okay. There's plenty of different ways. Sorry, I almost tripped there. That's pretty epic. So let me write out pseudocode for linear search. So I'm going to describe linear search to you using. So I'm going to describe linear search. I'm going to assume I have L, N, and X as inputs. So like I said, sometimes it's a little handy to write N as part of the input, but remember, you don't have to. You don't have to. Like, so say somebody's like, oh, well, like, why is N there? It doesn't have to be, because you can find that information out from L. But sometimes it's a little easier because then I don't have to define what L is. Sorry, N is. Sorry, I'm getting really excited here. So often it's important to describe the input. So it's array L of size N and a value X. And as output, as output, I am going to say it's position I such that L sub I is equal to X if X is in L, and -1 if X is not in L. So usually it's a good idea to give it a name, provide the inputs, describe them, give the output, describe that. That way everybody knows what the input and output are. Okay, so here's how I'm going to describe linear search to you. You might ask, Dan, why are you doing it this way? You'll see why in a moment, because there's a lot of ways I can write this down. I'm going to start off with a variable I. I'm going to declare it, and I'm going to assign it a value 0. I'm going to use this arrow to say I'm going to define and assign it the value 0. So you may know of other notations. You may have seen this one with a colon with an equal sign. This is define. This is also fine to use. So if you like that syntax, you can use that too. There's a lot of different ways you could do this. I would recommend not using equals, like equals like this, because that literally means equals. In a programming language, you'll commonly see this as assign. This means assign, that means assign or define. This, however, means literally equals, right? So we have to be careful. So I'd recommend avoiding that. However, if you do use this, you make sure that you use a programming-like syntax, so where you have equal to being two equal signs. Is that clear to everybody? So that's just an example of assignment. And I'm going to make a while loop. So I'm going to make go while I is less than n, and L sub I is not equal to x. We're going to do the following. So you might use braces or curly braces or curly brackets to enclose this, just like you would in programming language. But I'm not to, because I only have one line. So I'm going to assign I to be I plus 1 in my while loop. It's worth noting that I am technically making one assumption with the way I've written this. I'm technically assuming short circuiting exists in my pseudocode. So if, for example, it evaluates this before it evaluates that over there, because of course L sub n does not exist in my array. So if you're wondering about that, I'm assuming short circuiting exists in my pseudocode here. And then I'm going to say after my while loop. So sometimes people like to put a little bracket like this. Some people like using curly braces. You could do any of these things. So I'm going to say if I is equal to n, then return -1. Else I'm going to return I. And there's my pseudocode. So if you read this, you'd probably see no problems with, other than technical specifications. You could look at this and say, oh, well, that looks kind of like a program. I could see how I could probably implement this. But it's worth noting that as algorithms get more complicated, sometimes the steps that somebody might write in pseudocode might also get more complicated. But is everybody okay with this pseudocode that I wrote here? Is it clear? And keep in mind, if you do not like the fact that I wrote this assuming some specification, you can always put that L sub I not equal to x in an if statement inside the loop. It's easy enough. But it's also worth noting you also have to be careful, right? You have to make sure it exits the loop with a break, right? I'll think about that. But anyways, so that's an example of some pseudocode. And now what I would like to do is I would like to describe to you how we can try to prove the correctness of, say, linear search. So I got to talk briefly about proof of correctness. And believe it or not, we've talked about most of the framework already. So you're going to find I'm going to be kind of swift with this, and we'll try to get right to talking about a proof. So I just want to make one remark before I get to that. Is really built around this framework I just talked about previously. So you may recall that I have a set of problem instances, right? And they all get fed to this algorithm. And I assume if the algorithm if I solve the problem, that every time I feed one of these problem instances to my algorithm, so the inputs, of course, that means that if it always produces correct output, then means that it's correct all the time, right? So how do I know if an algorithm actually is incorrect? It doesn't actually work the way it's supposed to be claimed to be doing, right? How do I ensure or check that? So think about it and put it in the chat. So just as a remark, so somebody came along to you and tell you, I have this great algorithm and it solves this problem. What's the first thing you might try to do to tell them, no, it actually doesn't work? You test it, but what do you do actually when you test? Yeah, you try justifying, but what do you exactly, counterexample. You present a counterexample. So you just have to present a single counterexample, because you'll notice that my definition here of correctness requires that every single one of these problem instances, when I feed it to the algorithm, it produces correct output, right? So what does it mean when I want to tell you, no, it doesn't work? That means all I have to do is find one of these problem instances, one of these issue ones, so that I feed it to the algorithm, it doesn't produce correct output. That's all I have to do. A so-called counterexample. So to disprove the correctness of an algorithm, let's all say correctness. To disprove the correctness of an algorithm, present a counterexample. So just to clarify, a counterexample would just simply be that, so this would just be a problem instance that produces, when given to the algorithm, outputs a wrong answer. So all you do is you just find one counterexample. You can find, if you really want to show them that its thing is really just terrible, you could even go crazy and be like, okay, I'll present a whole set of instances that don't work. And in fact, there is some intuition behind doing something like that. Because sometimes when you find a whole collection of instances where an algorithm fails to work, there might be a way of remedying and fixing it for all those things. Just like when you do debugging. You might find a problem in, say, a set of code. But at the same time, if you identify all of the problem ones, you might be able to fix the whole thing, right? So there is a mathematical but also a practical intuition behind this. Is that clear to everybody? So all you do is you just find one of these problem instances that just does not work when you give it to the algorithm. It doesn't do what's supposed to happen. It's supposed to produce correct output. This may be because the algorithm runs on forever. It may be the case that it doesn't do what it's supposed to do, right? Because you'll make a claim about this. Okay, so let me just summarize what I want to talk about, and then we'll talk more about this next time. Is an algorithm is correct. So just to re-summarize this, because I really need to hammer this in, is correct if for every instance, it, as in the algorithm, it produces correct output. I'll hit on this point a lot of times because it's very important. I need to, so it's an excellent question. Is there a way to find a counterexample? The unfortunate answer is that it always depends on two things, the problem itself and the algorithm in question. It's not as satisfactory of an answer you might find, but it's very much like that. But you try to figure out what the algorithm does, you study the problem, and then you see, is there something about this algorithm it does not take into consideration? And that's oftentimes what you do. And it's actually quite fascinating for somebody that may be more mathematically inclined in this class. They might be already familiar with this idea, this idea that you just break things. So not literally, don't take pieces of paper and just rip them in half. I mean, like an actual, the idea. So you're going to try your best to break the ideas by trying to find ways that it doesn't work. So you just go back to the definitions, you go look at the algorithm, and you see, is there something that this algorithm does that doesn't actually match up with what the problem is about? So say there might be some special condition a problem has. It may be the case that there exists some problem instance that doesn't actually fit that bill. Doesn't fit the bill. And that's very common when people try to prove theorems. You're going to find that there's a very close connection between the correctness of an algorithm and this activity that we would normally do with proving mathematical claims. They're quite closely entwined. They're essentially the same activity. So just want to summarize one thing, and then we'll wrap things up here, okay? And then we'll talk more about proof of correctness next time. So I want to summarize a couple of quick things here. Okay, so we say, to show an algorithm is correct, we prove two things. We need to prove two things at some point. So the first one is that it terminates in finite time. Like I said earlier, if it doesn't terminate, it can't produce output, right? So it has to terminate in finite time. And of course, the most important one is the algorithm produces correct output, right? So just as a remark, there are some standard ways that people go about this, and it's very much like proving any kind of mathematical claim, just this has a quite rigid structure to it. So common techniques that get used. So some common techniques, because you're going to see a lot of different ways you can prove the correctness of algorithms in this course. But I'm going to try to expose you to plenty of different ones, but not all at once, because I feel like that really is kind of not as fun as I would hope it would be. So some common techniques are, of course, direct. So of course, a direct proof would be where you would exhaust all the things that the algorithm does and make observations about what the algorithm does in respect to that case. So you might know this as proof via cases. So we'll be doing that when we look at our correctness for linear search in our example here. You may also know of indirect proofs, possibly. So you would use, for example, contradiction. Now, if you've never seen these before, fortunate thing is I will talk about them in class. However, I wrote a really, really great collection of examples, and I spent a lot of time in my mathematical preamble about this. If you've never seen these ideas before, and if you want to get yourself cozy with them, I have plenty of examples. Okay. And the last one is mathematical induction. So, depending on time in this class, I will talk possibly about mathematical induction with respect to correctness. I may even post an example, so if those that really want to see it, I will probably post one of these. There's also another technique called loop invariance, or so-called proof by invariance. I may not have time to talk about that, but you're going to get the general gist of that idea throughout this class. We'll see plenty of examples of it. So next time, we're going to try proving the correctness of linear search. We're going to probably take a direct approach in class. That being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.